Have you ever paused to consider just how much we don't know about the universe? We've sent rovers to Mars and peered into the hearts of galaxies, yet space is still brimming with mysteries that have puzzled scientists for generations. We're talking about strange signals, unexpected encounters, and cosmic events that simply don't fit neatly into our current understanding of physics. In this video, we're embarking on a cosmic journey to explore 25 of the most baffling, unexplainable events in space history. These are the head-scratchers, the anomalies, the moments that keep the universe's enigma alive. Get ready to dive deep into the unknown and perhaps question everything you thought you knew about the final frontier. Our first unexplained event takes us back to 1977, to the Big Ear radio telescope at Ohio State University. It was here that astronomer Jerry Amon was reviewing printouts of radio data from a scan of the skies when he spotted something truly remarkable. A sequence of letters and numbers stood out, a signal so strong and so unusual that he circled it and wrote, "Wow." Next to it, now, this wasn't just any random blip. The wow signal lasted for precisely 72 seconds, the exact duration that the Big Ear could observe a specific point in the sky due to Earth's rotation. What made it even stranger was its frequency. It was detected at 1420 MHz, a frequency near the 21-centimeter line, which is the frequency at which neutral hydrogen atoms emit radio waves. This frequency is internationally protected for astronomical use specifically because it's considered ideal for interstellar communication. It cuts through the noise. The signal appeared to come from the direction of the constellation Sagittarius, near the star group Chi Sagittarii. Since that incredible night, countless hours have been spent trying to detect the signal again. Radio telescopes around the world have searched that patch of sky, but the wow signal has never been heard from again. This lack of repetition is one of the most perplexing aspects. Was it a one-off cosmic event? Could it have been terrestrial interference, though its characteristics seem to rule that out? Or, as tantalizing as it sounds, was it a genuine broadcast from a civilization far beyond our own? The silence that followed only deepens the mystery surrounding this solitary, powerful flash of radio waves. Moving on from the silent mystery of the wow signal, we journey back in time to June 30th, 1908, over the vast, remote forests of Siberia. On that morning, something truly extraordinary and terrifying happened near the Tunguska River. A massive explosion ripped through the sky, an event so powerful it flattened some 80 million trees across an area of over 2,150 square kilometers. That's larger than many major cities. Yet, despite the immense destruction, there was no impact crater found. None. Eyewitnesses scattered across the sparsely populated region described a blinding light brighter than the sun, streaking across the sky, followed by intense heat and a deafening roar. The shockwaves generated were so strong they knocked people off their feet hundreds of kilometers away and registered on seismic stations across Eurasia. Imagine a force equivalent to several megatons of TNT detonating high above the ground. For decades, the Tunguska event remained shrouded in speculation. Early scientific expeditions to the site faced incredible logistical challenges due to its remoteness. When they did arrive, they found the eerie scene of trees charred and blown down in a radial pattern, emanating from a central point where, again, there was no crater. This absence of an impact site is a key piece of the puzzle, strongly suggesting that whatever caused the blast didn't actually hit the ground. The leading scientific theory today is that the event was caused by the airburst of a large meteoroid or a fragment of a comet breaking up in the Earth's atmosphere. The object, estimated to be tens of meters across, vaporized before reaching the surface, releasing its immense energy in the atmosphere. This would explain the lack of a crater and the widespread destruction from the atmospheric shockwave. However, even this widely accepted theory leaves questions. The exact nature of the object, was it stony like a meteoroid or icy like a comet fragment, is still debated, and despite extensive searching, very little physical evidence of the object itself has ever been recovered. The Tunguska event remains a powerful reminder of the devastating potential of cosmic impacts and the lingering mysteries they can leave behind. Leaving behind the earthly impact of Tunguska, let's turn our gaze towards our closest celestial neighbor, the Moon. For centuries, people have reported seeing strange, fleeting flashes of light, glows, or changes in color on the lunar surface. These aren't just scattered, unreliable anecdotes, they're what astronomers refer to as transient lunar phenomena, or TLP. We're talking about observations that date back hundreds of years, long before telescopes could offer detailed views. Imagine monks in the Middle Ages noting a reddish glow on the Moon, or later astronomers in the 1700s reporting bright, moving lights. These aren't just one-off sightings, there's a long, documented history of these mysterious lunar flashes. Fast forward to the age of modern astronomy, and the observations continue, though with more scientific scrutiny. While some early reports might be attributed to atmospheric effects or even simple overestimation, many TLP events have been witnessed by multiple observers, sometimes even through telescopes. In more recent times, scientists have attempted to set up dedicated monitoring programs to catch these elusive flashes in action, using specialized equipment to analyze any detected light and pinpoint its location. Despite these efforts, catching a TLP is incredibly difficult due to their unpredictable nature and brief duration. So, what could possibly be causing these ephemeral events on the seemingly unchanging surface of the Moon? Several explanations have been proposed over time. One possibility is lunar outgassing, the release of gases from within the Moon's interior through cracks or vents. This could potentially create temporary fogs or even electrical discharges that manifest as glows or flashes. Another leading candidate is meteoroid impacts. The Moon is constantly bombarded by tiny particles from space, and while larger impacts create visible craters, smaller ones could generate brief flashes of light and heat upon hitting the surface. Electrostatic phenomena are also considered, perhaps related to lunar dust being disturbed or charged. However, the puzzle of TLP lies in the fact that none of these single theories seem to fully explain all the reported sightings. Some flashes appear too bright to be typical meteoroid impacts, while others last too long for a simple outgassing event. The variety in the reported phenomena, from quick pinpricks of light to larger, diffuse glows, makes it challenging to attribute them all to a single cause. It leaves us with a lingering question about what exactly is happening on the lunar surface that causes these brief, unexplained displays, reminding us that even the most familiar object in our night sky holds its own secrets. From the mysterious flashes on our cosmic doorstep, the Moon, we now zoom out to the truly vast scale of the universe. Imagine entire galaxies, colossal collections of stars, gas, and dust, all moving through space. For decades, astronomers observed something puzzling. Galaxies, including our very own Milky Way, weren't just drifting randomly. They seemed to be flowing, pulled towards a particular region of space. This observation led to the concept of something immense and unseen, a gravitational powerhouse dubbed the Great Attractor. Located roughly 150 to 250 million light-years away in the direction of the constellations Triangulum, Austral, and Norma, this region exerts such a powerful pull that it influences the motion of galaxies across a significant swath of the cosmos, a vast structure known as the Laniakea supercluster. We inferred its existence not by seeing it directly, but by meticulously measuring the velocities of countless galaxies and realizing they had a preferred direction of motion, as if being drawn by an invisible hand. The more distant the galaxy, the less influenced it appears to be, but within our galactic neighborhood, the pull is undeniable. Pinpointing exactly what the Great Attractor is has been an enormous challenge for astronomers. The fundamental problem is that it lies behind the disk of our own Milky Way galaxy. Think of it like trying to see a distant object on the horizon when there's a thick fog or a dense forest right in front of you. The stars, gas, and dust within our galaxy absorb and scatter light, making it incredibly difficult to observe anything clearly in that direction using visible light telescopes. This region has effectively been a blind spot in our astronomical observations. Despite this hurdle, scientists have used other methods, like observing in infrared and radio wavelengths, which can penetrate some of the galactic dust, and by studying the cosmic microwave background radiation to try and peer through the cosmic veil. These studies have revealed a complex region, not likely a single massive object, but rather a concentration of mass, perhaps a supercluster of galaxies far larger and denser than any we've directly observed, or perhaps something even more exotic that we don't yet fully understand. The precise distribution and nature of the mass within the Great Attractor are still subjects of intense research and debate. Its immense, unseen gravitational influence continues to shape our understanding of how structures form and move on the largest scales of the universe. Shifting our focus from the deep pull of cosmic structures, let's talk about something incredibly brief, yet astonishingly powerful: fast radio bursts, or FRB. Imagine a flash of radio waves so fleeting it lasts only a few milliseconds, but in that instant it can release more energy than the sun does in an entire day. These are cosmic phenomena that have been puzzling astronomers since their first confirmed detection in 2007. The initial discovery, made by astronomer Duncan Lorimer and his team while reviewing archival data from the Parkes Observatory in Australia, was so unexpected it was initially met with skepticism. Was it a glitch, terrestrial interference? But as more powerful radio telescopes came online and scientists specifically searched for these signals, it became clear that FRBs were real and they were coming from far beyond our own galaxy. What makes FRBs so mysterious? Their incredibly short duration is one factor. Catching them in the act is like trying to photograph a lightning strike in a hurricane. Another is their incredible energy output. To generate such a powerful pulse in such a short time requires an extreme astrophysical event. Early theories ranged from merging black holes to evaporating primordial black holes, or even signals from advanced alien civilizations, though the latter remains highly speculative. The leading candidates for the origin of FRBs today often involve neutron stars, the incredibly dense remnants of collapsed stars. Specifically, highly magnetized neutron stars called magnetars are thought to be capable of producing such intense bursts of radio waves. However, just when scientists thought they might be closing in on an explanation, another layer of complexity emerged: repeating FRBs. In 2016, the first repeating FRB was discovered. This meant that the same source in a distant galaxy was emitting multiple bursts, not just a single one-off event. This ruled out explanations like cataclysmic explosions, which would destroy the source. The existence of repeaters strongly pointed towards a compact object, like a neutron star, that could survive and continue to emit these powerful pulses. Yet, even with the discovery of repeaters and the focus on magnetars, the precise mechanism by which these objects generate such immense radio energy is still not fully understood. Every new FRB discovery, whether it's a single burst or a repeating source, provides another clue in this cosmic puzzle, reminding us that the universe is still full of surprises, broadcasting enigmatic signals from the depths of space. From the distant reaches of fast radio bursts, let's turn our attention back to something much closer to home, yet shrouded in its own kind of mystery and legend: the so-called Black Knight satellite. This is an enduring urban myth that speaks of an ancient alien spacecraft orbiting Earth, silently observing us for thousands, maybe even tens of thousands of years. While the scientific community regards this as folklore, the story has captured imaginations and persists in popular culture. Where did this intriguing tale begin? Its roots aren't in a single, clear observation, but rather a fascinating convergence of unrelated events and misinterpreted information over many decades. One thread traces back to the late 1920s when amateur radio operators reported hearing strange, delayed radio echo signals they sent out returning seconds or even minutes later. These were known as long-delayed echoes, or LD, and while they remain a phenomenon not fully understood, they were later erroneously linked to the Black Knight. Another crucial element that fed the legend came in the 1960s. During early space missions, engineers observed unusual objects in polar orbits that pass over the Earth's poles rather than its equator. These orbits were less common at the time, and some of these objects were unidentified. Combine these observations with the persistent LD mystery and add a sprinkle of Cold War-era speculation about surveillance satellites, and you start to see how a narrative could form around a singular, unknown object. The term Black Knight itself seems to have emerged much later, possibly in the 90s, solidifying around these earlier disparate pieces of the puzzle. So, what are the scientific explanations for the phenomena that got woven into the Black Knight story? The long-delayed echoes, while still partly mysterious, aren't attributed to an orbiting satellite. Theories include complex interactions of radio waves with the Earth's ionosphere or even reflections from clouds of plasma in space. As for the unidentified objects in polar orbits observed in the early days of spaceflight, these were almost certainly pieces of space debris, perhaps fragments from rocket bodies or discarded equipment. As space activity increased, so did the amount of orbital junk. What was once a puzzling observation of an object in an unusual orbit became a standard part of space tracking. Despite the clear, non-extraterrestrial explanations for the elements that comprise the Black Knight narrative, the legend endures. Perhaps it's the appeal of a hidden observer, a silent sentinel from beyond, or maybe it's just the human desire for a good mystery. While there is no scientific evidence of an ancient alien satellite, the story of the Black Knight serves as a fascinating example of how unconnected events and a bit of speculation can coalesce into a persistent and captivating piece of modern mythology. Leaving behind the terrestrial myths and journeying deep into interstellar space, let's look at a truly breathtaking yet perplexing feature observed by the Hubble Space Telescope, the Pillars of Creation. You've likely seen those iconic images, towering columns of cosmic gas and dust within the Eagle Nebula, birthplace of new stars. They are breathtakingly beautiful. But lurking near these celestial giants, Hubble captured something else, something strange and ethereal, often described as a spook or a finger. This peculiar, wispy structure seemed to float in the cosmic void near the base of the pillars. Its appearance was unlike anything immediately familiar within the nebula. Imagine a faint, elongated phantom limb reaching out from the stellar nursery. When astronomers first observed this spectral feature, it caused considerable confusion. What was this strange projection? Was it a separate object, a different type of cosmic phenomenon altogether, or somehow related to the mighty pillars themselves? The initial images raised more questions than they answered, prompting a closer look at this unexpected addition to an already famous celestial landscape. Subsequent, more detailed observations and careful analysis of this spook provided some potential clues, allowing astronomers to develop theories about its nature. It became clear that this ethereal structure wasn't entirely disconnected from the activity around the Pillars of Creation. One leading theory suggests that this finger could be an ionization front being sculpted by intense radiation from nearby young, massive stars. These powerful stars emit streams of charged particles known as stellar winds and intense ultraviolet light. This energy can ionize the gas and dust in their surroundings, causing it to glow and pushing it outwards. Picture the stellar wind as a cosmic bulldozer, shaping the less dense material into these elongated, finger-like forms. Another possibility is that it represents a denser knot of gas and dust that is resisting the erosive effects of the stellar radiation and wins more effectively than the surrounding material, leaving it standing out like a solitary spire. However, even with these plausible explanations, the exact formation mechanism of this specific spook and its precise relationship to the larger pillars of creation remain subjects of ongoing research and debate among astrophysicists. It serves as a subtle reminder that even in well-studied and seemingly familiar cosmic landmarks, there are still intricate details and processes that continue to challenge our understanding. From the visible wonders of nebulae, our journey now takes us to the invisible, the unknown that makes up most of the universe. Imagine looking out at the cosmos, seeing stars, galaxies, and gas clouds, and then being told that everything you can see is just a tiny fraction of what's actually there. This brings us to one of the biggest mysteries in modern astronomy: dark matter. It's not dark in the sense of being black or shadowy. It's dark because it doesn't interact with light or any form of electromagnetic radiation. You can't see it, you can't feel it, and it doesn't emit, absorb, or reflect light, making it incredibly difficult to detect directly. Yet, the evidence for its existence is overwhelming, coming from multiple lines of astronomical observation. It's estimated that dark matter accounts for roughly 85% of the total matter in the universe. Think about that: the vast majority of the stuff out there is completely invisible to us. So, if we can't see it, how do we know it's there? The strongest evidence for dark matter comes from its gravitational effects on visible matter. One of the key pieces of evidence is the rotation curves of galaxies. If the only matter in a galaxy were the stars and gas we can see, then stars on the outer edges should orbit much slower than those closer to the center, just like planets further from the sun move slower. However, observations show that stars on the outer edges of galaxies orbit at surprisingly high speeds, as if there's a lot more mass pulling them in than is visible. This extra gravitational pull is attributed to a halo of dark matter surrounding the galaxy. Another powerful piece of evidence comes from gravitational lensing. This is a phenomenon predicted by Albert Einstein's theory of general relativity, where massive objects bend the fabric of spacetime, causing light from objects behind them to be distorted or magnified, much like a lens. When astronomers observe the light from distant galaxies being warped or bent by foreground galaxy clusters in ways that can't be explained by the visible matter alone, it points to the presence of significant amounts of unseen mass dark matter contributing to the gravitational pull. The mystery of what dark matter actually is continues to drive intense scientific investigation. It's not just regular matter like protons and neutrons which make up stars and planets, because if it were, we would see it interacting with light. This means it must be some form of exotic, non-baryonic matter. Scientists are actively searching for theoretical particles that could fit the description of dark matter. One leading candidate is the weakly interacting massive particle, or WIMP, a hypothetical particle that would interact with normal matter only through gravity and possibly the weak nuclear force, hence the name weakly interacting. Other possibilities include actions, sterile neutrinos, or even entirely new types of particles not yet predicted by our standard model of particle physics. Experiments deep underground, shielded from cosmic rays, are attempting to directly detect dark matter particles as they might occasionally collide with atomic nuclei. Particle accelerators like the Large Hadron Collider are also searching for evidence of these hypothetical particles by trying to recreate the conditions under which they might be formed. The profound mystery remains: what constitutes this unseen, dominant force that shapes the very structure of the cosmos? If dark matter is the invisible scaffolding of the universe, controlling how galaxies rotate and cluster, then dark energy is something else entirely, an even more profound enigma. Imagine the universe not just expanding, but the expansion itself speeding up, accelerating over time. This astonishing discovery was made in the late 1990s by two independent teams of astronomers studying distant supernova, specifically Type Ia supernova. These particular types of stellar explosions are incredibly useful because they act like standard candles. They always reach roughly the same peak brightness, making them reliable tools for measuring cosmic distances. By comparing how bright these distant supernovae appeared to how bright they should be, astronomers could figure out how far away they were, and by looking at the redshift of their light, how much their light had been stretched to longer, redder wavelengths by the expansion of the universe, they could determine how fast the universe was expanding at different points in cosmic history. What they found was completely unexpected. The expansion wasn't slowing down due to gravity, as was previously thought. It was actually accelerating. This implied the existence of a mysterious force pushing the universe apart, counteracting gravity's pull on the largest scales. This force was given the name dark energy. The discovery of dark energy was so groundbreaking it earned the scientists involved the Nobel Prize in Physics in 2011. But knowing it exists and understanding what it is are two very different things. Dark energy is estimated to make up roughly 68% of the total energy and matter content of the universe, even more prevalent than dark matter. Yet its nature remains a complete mystery. One leading theoretical idea is that dark energy is a cosmological constant, a concept first introduced by Albert Einstein, though he later abandoned it. In this view, dark energy is an intrinsic property of empty space itself, a constant energy density that doesn't dilute as the universe expands. Thus its repulsive effect increases over time and causes the accelerating expansion. Another possibility is that dark energy is a dynamic field, something that changes over time and space, sometimes referred to as quintessence. This would be a more complex explanation, potentially linked to other fundamental forces or particles. Then there are even more radical ideas, suggesting that perhaps our understanding of gravity on cosmic scales is incomplete, and what we perceive as dark energy is actually a manifestation of modified gravity. Currently, observations are consistent with the cosmological constant model, but the data isn't precise enough to definitively rule out other possibilities. Dark energy represents a fundamental gap in our understanding of the cosmos, arguably the most significant puzzle in modern physics and cosmology. It's the unseen force that dictates the ultimate fate of the universe. If dark energy is pushing the universe apart and dark matter is holding galaxies together, then another cosmic puzzle asks a question that hits much closer to home: are we alone? This brings us to one of the most profound and unsettling questions in space history, captured by the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The paradox highlights a stark contradiction. On the one hand, based on the sheer number of stars and planets out there, billions in our galaxy alone, and billions of galaxies in the observable universe, it seems highly probable that life, even intelligent life capable of forming civilizations, should exist elsewhere. With so many potential homes for life, the odds seem stacked in favor of extraterrestrial civilizations emerging. So, if intelligent life is likely common in the cosmos, why haven't we found any convincing evidence of it? Why haven't we detected radio signals, observed megastructures built by advanced races, or encountered visitors? The silence is deafening, and that's the heart of the Fermi paradox. It's the unsettling gap between the high statistical probability of alien civilizations and the complete lack of observational proof. This profound silence has led to a wide range of potential explanations, often called solutions to the paradox, although none are definitively proven. One set of solutions suggests that intelligent life is, in fact, incredibly rare. This could be due to a series of highly improbable steps required for life to arise, evolve complexity, and then develop technology capable of communicating across interstellar distances, what's sometimes referred to as the Great Filter. Perhaps abiogenesis, the process of life arising from non-living matter, is exceedingly rare, or maybe the jump from simple life to complex, multicellular organisms is the bottleneck. Another possibility within this rarity category is that civilizations don't last very long. They might reach a technological stage where interstellar communication is possible, but then quickly succumb to self-inflicted disasters like nuclear war, environmental collapse, or even unintended consequences of advanced technology like rogue artificial intelligence. This is the chilling idea that technological civilizations inevitably self-destruct before they have a chance to meet others. Another set of explanations proposes that civilizations do exist, but they are deliberately undetectable or choose not to communicate. Perhaps advanced civilizations follow a prime directive, choosing not to interfere with less developed species like our own, observing us silently from a distance, similar to a cosmic zoo hypothesis. They might have moved beyond radio communication to methods we can't yet detect, or they could be so far ahead technologically that their activities are simply incomprehensible to us. There's also the grim possibility that the universe is a dangerous place, and advanced civilizations actively hide themselves to avoid attracting unwanted attention from hostile entities. Or consider the idea that they simply aren't interested in communicating with us. Perhaps they've found more engaging ways to spend their time or energy. The implications of the Fermi paradox are vast and humbling. Does the silence mean we are truly alone, a cosmic anomaly? Or does it suggest a future where civilizations face inevitable barriers or choose paths that make contact impossible? The lack of an answer forces us to confront our place in the universe and the potential challenges that might lie ahead for humanity. The emptiness of the cosmic airwaves compels us to look deeper, both into space and potentially into ourselves. From the vast philosophical implications of the Fermi paradox, let's bring things back to a specific and very famous image captured much closer to home. Remember the 1970s, the height of space exploration. NASA's Viking program was sending orbiters and landers to Mars, giving us our first truly detailed views of the red planet. And in 1976, the Viking 1 orbiter sent back a picture that ignited imaginations around the world. It was an image from the Cydonia region of Mars, and within it, something extraordinary seemed to emerge, a formation that looked uncannily like a human face staring back at the camera. The image quickly spread, appearing in newspapers and on television screens. People were captivated. Was this proof of ancient Martian civilization, a monument left behind by a visiting species? The idea of a face on Mars, a potential signature of intelligence on another planet, became deeply embedded in popular culture and fueled endless speculation and debate. However, while the public fascination soared, scientists approached the image with cautious analysis. They understood how light and shadow, coupled with our brain's tendency to recognize patterns, a phenomenon called pareidolia, could create convincing illusions. The initial Viking images were relatively low resolution, and the angle of the sun, casting long shadows, played a significant role in making the feature look like a face. Geologists pointed out that Mars is home to numerous mesas and buttes, large rock formations that are often eroded into unique shapes. The suspected face appeared to be just such a feature. Over the following decades, as space exploration technology advanced, later missions provided the opportunity to revisit the Cydonia region with much higher resolution cameras. The Mars Global Surveyor, launched in 1996, captured detailed images of the same feature, and these pictures told a clearer story. The higher resolution images revealed a natural, geological landform, a mesa with slopes, ridges, and textures entirely consistent with erosion and natural processes. The face was gone, replaced by a more mundane, though still impressive, Martian mesa. Subsequent images from other missions, like the Mars Reconnaissance Orbiter, further confirmed this geological reality. Despite the scientific explanation and the clearer imagery, the face on Mars retains a stubborn grip on popular interest. It stands as a compelling example of how striking visual anomalies can capture the public imagination, even when scientific evidence points to a more prosaic explanation. It reminds us of our innate desire to find meaning and potential evidence of life beyond Earth, sometimes even in the play of light and shadow on a distant world. Stepping away from the rocky features of Mars, let's consider another visual anomaly, though one observed from Earth and linked to atmospheric rather than geological processes. This brings us to the perplexing phenomenon known as the Hessdalen lights. For many years, residents of the Hessdalen Valley in Norway have reported seeing strange, unexplained lights in the sky. These aren't typical stars, aircraft, or even known meteorological phenomena. The lights vary in appearance. Sometimes they're bright white or yellowish flashes. Other times they appear as slower-moving, glowing spheres of red or blue light. Some reports describe the lights hovering, moving erratically, or even changing shape. The frequency of these sightings peaked in the early 1980s, attracting significant attention and sparking numerous investigations. Imagine locals describing these silent, mysterious lights dancing above the valley, sometimes appearing for just a few seconds, at other times remaining visible for over an hour. These consistent reports from a specific geographical location set the Hessdalen lights apart from isolated UFO sightings and prompted a dedicated scientific effort to understand them. In response to the numerous sightings, a project called Project Hessdalen was established in 1983 by Norwegian scientists. Their goal was to systematically monitor the valley and try to capture the lights using a variety of instruments, including cameras, radar, and spectrum analyzers, which can measure the different wavelengths of light. Over the years, Project Hessdalen has collected a considerable amount of data. They have recorded sightings, taken photographs, and even managed to analyze the spectrum of some of the lights. The data confirms the existence of these luminous phenomena, dispelling any doubt that people are indeed seeing something unusual. However, the data has not yet provided a single, definitive explanation that accounts for all the observed characteristics of the lights. Several scientific hypotheses have been put forward to try and explain the Hessdalen lights, but none have achieved universal acceptance or been conclusively proven. One prominent theory suggests that the valley's unique geology might play a role. The valley is known to have a concentration of certain minerals, including iron and zinc. One hypothesis proposes that these minerals, perhaps interacting with the valley's underground river system and electrical currents in the Earth's crust, could somehow generate an electrochemical reaction that produces visible light. Another possibility involves plasma, a state of matter where gas is ionized and highly energetic. Perhaps conditions in the Hessdalen Valley are somehow conducive to the formation of atmospheric plasma that manifests as these moving lights. Other ideas include the combustion of airborne dust particles containing rare Earth elements, or even some complex interaction between magnetic fields and atmospheric conditions. The challenge in definitively explaining the Hessdalen lights lies in their unpredictable nature, relatively rare occurrence, and the difficulty of being in the right place at the right time with the necessary scientific equipment. While most scientists believe the phenomenon has a natural, albeit complex, explanation rooted in the valley's geochemistry and atmospheric conditions, the exact mechanism remains elusive. The Hessdalen lights continue to be a captivating, ongoing mystery, a reminder that even on our own planet, unexplained luminous events can persist, defying simple explanations. Leaving the puzzling lights closer to home behind us, let's journey back out to the stars, to a moment in 2015 that briefly sent ripples of excitement through the SETI community, the search for extraterrestrial intelligence. This event centered around a Sun-like star located about 94 light-years away in the constellation Hercules, a star designated HD 164595. It's known to host at least one planet, a Neptune-sized world, making it a potential, though not ideal, candidate for hosting life as we know it. The intriguing part came when astronomers using the Ratan 600 radio telescope in Russia detected a strong, fleeting radio signal coming from that direction. The signal itself was powerful, reportedly about 10 times stronger than typical radio interference. This power, combined with its narrow bandwidth, meaning it was concentrated at a specific frequency, unlike the broad spectrum of natural cosmic radio sources like pulsars or quasars, made it particularly interesting. These characteristics are sometimes cited as potential indicators of an artificial, rather than natural, origin. When the detection became more widely known in 2016, it naturally generated a buzz. Could this finally be it? Could this be the first confirmed signal from an extraterrestrial civilization? The initial reports sparked discussions about the possibility of a deliberate beacon or even accidental leakage radiation from advanced technology around HD 164595. However, as is often the case with potential cosmic signals, the excitement was tempered by the need for verification. The crucial next step was follow-up observations. Astronomers around the world, including those involved in SETI projects using powerful instruments like the Allen Telescope Array and the Green Bank Telescope, quickly pointed their dishes towards HD 164595 to try and detect the signal again. The outcome, silence. Despite extensive searching with more sensitive equipment, the signal was never redetected. This lack of repetition is a significant factor in analyzing transient signals. If it were a persistent broadcast from an alien civilization, it would likely still be there. The failure to confirm the signal through repeated observations, combined with further analysis of the original data and potential terrestrial sources, led most of the scientific community to conclude that the signal was, unfortunately, likely the result of radio frequency interference here on Earth. Radio telescopes are incredibly sensitive instruments, and they can pick up signals from human technology satellites, ground-based transmissions, even microwave ovens that can sometimes mimic the characteristics of a potential extraterrestrial signal. While the initial detection from HD 164595 created a brief, exhilarating period of speculation about a potential alien message, the subsequent lack of confirmation firmly placed it in the category of probable interference, adding another chapter to the complex and often challenging search for signals from other worlds. From the potential signals of alien life, we turn our attention to something undeniably cosmic and incredibly energetic: pulsars. Imagine a star that has lived out its life, exploded in a supernova, and collapsed into an object so dense, a teaspoon of its matter would weigh billions of tons here on Earth. This is a neutron star, a celestial powerhouse. Many neutron stars spin incredibly fast, some rotating hundreds or even thousands of times a second. As they spin, they emit beams of radiation from their magnetic poles. If these beams sweep across Earth, we detect them as regular pulses, much like the beam from a lighthouse. This is why they are called pulsars, because of these precise, repeating pulses. For the most part, these pulses are remarkably stable, acting like cosmic clocks, so much so that scientists can use them for incredibly accurate timing experiments. However, these cosmic clocks aren't always perfectly reliable. Every now and then, a pulsar does something truly unexpected and baffling. It suddenly and inexplicably speeds up its rotation rate. This is what astronomers call a glitch, and one of the most famous examples of this phenomenon comes from the Crab Nebula pulsar, the remnant of a supernova observed by Chinese astronomers in the year 1054. The Crab pulsar is known for having frequent and relatively large glitches compared to other pulsars. Just imagine this incredibly dense object spinning hundreds of times a second suddenly gives a little cosmic twitch and spins noticeably faster. While the change in speed is tiny in terms of its overall rotation, it's a significant and sudden deviation from its normally predictable behavior. So, what could possibly cause these massive, dense objects to suddenly speed up their spin? The leading theories point to events happening deep inside the neutron star. One prominent explanation is a sudden transfer of angular momentum from the inner layers of the neutron star to its crust. Neutron stars are thought to have different layers, including a solid outer crust and a superfluid interior. Picture the interior superfluid rotating a bit faster than the crust due to friction over long periods. A glitch might occur when the crust can no longer withstand the stress built up by this differential rotation, and it cracks or quakes. This starquake could cause a rapid coupling between the faster spinning interior and the crust, transferring angular momentum outward and causing the crust, and thus the pulsar's emission, to spin faster. Another theory involves vortex unpinning within the superfluid interior. The vortices in the superfluid are thought to be normally pinned to the inner crust. A glitch could happen when these vortices suddenly become unpinned and move outward, transferring their angular momentum to the crust. Understanding these glitches is crucial because they provide rare glimpses into the extreme, exotic physics happening within these highly compressed objects, conditions we can't replicate in any laboratory on Earth. Each glitch is like a tiny, violent earthquake on a neutron star, offering a window into its hidden interior. If the silence highlighted by the Fermi paradox leaves us wondering where everyone is, perhaps the best way to approach the question is to break it down. This is precisely what astronomer Frank Drake attempted to do in 1961 with a simple yet profound formula, now known as the Drake equation. Think of it not as a rigid mathematical calculation that yields a precise number, but rather as a framework, a way to organize our ignorance and stimulate scientific discussion about the factors that might influence the number of detectable extraterrestrial civilizations in our galaxy. The equation itself is a series of terms multiplied together, each representing a different factor we need to consider. It looks something like this: N equals R star times Fp times Ne times Fl times Fi times Fc times L. At first glance, it might look intimidating, but let's break down what each of these variables represents. We start with R star, which is the average rate of star formation per year in our galaxy. We have a pretty good handle on this number thanks to decades of astronomical observations. Next is Fp, the fraction of those stars that have planets. Excitingly, thanks to missions like the Kepler Space Telescope, we now know that planets are incredibly common. We're talking billions of planets just in the Milky Way, so this variable is becoming less speculative. Then there's Ne, the average number of planets that can potentially support life per star that has planets. This often refers to planets within the habitable zone, where liquid water could exist on the surface, but it can also include worlds with subsurface oceans or other potential environments for life. While we're finding many exoplanets, determining which ones are truly habitable or have the right conditions for life is still complex. Here's where the equation really starts to delve into the realm of deep uncertainty and where things get speculative. The fourth term, Fl, is the fraction of those potentially habitable planets that actually develop life. This is a massive unknown. How does life begin? Is it an incredibly rare event, or does it arise relatively easily given the right conditions? We only have one example of life on Earth, so our understanding of abiogenesis, the origin of life from non-living matter, is limited. We simply don't know if life is a cosmic accident or a cosmic imperative. Following that is Fi, the fraction of planets with life that go on to develop intelligent life. Again, on Earth, intelligence as we define it arose only once in billions of years of life's history. Is intelligence a common evolutionary outcome or a rare path? And if it is rare, how rare? This is another term where we're essentially guessing. The final two terms are particularly relevant to the Fermi paradox. Fc is the fraction of civilizations with intelligent life that develop technology capable of releasing detectable signs of their existence into space, such as radio transmissions. Just because a civilization is intelligent doesn't mean they will develop or choose to use radio telescopes or broadcast powerful signals. They might communicate in ways we don't anticipate or can't detect. And finally, L is the length of time for which such communicative civilizations release those detectable signals into space. This is perhaps the most uncertain and potentially the most chilling variable. How long do technological civilizations typically survive after reaching a communicative stage? Do they last for millions of years, broadcasting their presence across the galaxy, or do they collapse or destroy themselves relatively quickly? War, environmental catastrophe, technological singularity, loss of interest in communication, there are many potential fates. The vast uncertainty in these latter variables FL, FI, FC, and especially L is precisely why the Drake equation doesn't give us a firm answer, but rather a range of possibilities that can span many orders of magnitude. If L, the lifespan of communicative civilizations, is very short, it could explain the Great Silence, suggesting that civilizations are fleeting sparks in the cosmic night. The Drake equation vividly illustrates how our lack of knowledge about the prevalence and longevity of life and intelligence beyond Earth directly underpins the mystery of why we haven't heard from anyone else. Following the mathematical framework of the Drake equation, let's consider another type of signal that has puzzled astronomers, but unlike fleeting radio bursts, this one seemed to be a constant rhythmic pulse from the depths of space. We're talking about the discovery of pulsars themselves and the initial bewilderment they caused back in 1967. Imagine PhD student Jocelyn Bell Burnell and her supervisor Anthony Hewish working with a newly built radio telescope designed to study quasars, distant energetic sources. They were looking for steady signals, but instead they started detecting something completely different. Incredibly regular pulses of radio waves repeating with astonishing precision, sometimes down to milliseconds. These signals were so precise, in fact, that they were initially code-named LGM-1, standing for Little Green Men 1, half-jokingly considering the possibility that they could be artificial signals from an alien civilization. The regularity was just that unnerving and unlike any known natural astronomical phenomenon at the time. This initial, tantalizing thought of extraterrestrial communication quickly gave way to intense scientific investigation. What could possibly produce such rapid, rhythmic pulses? The signals were unlike anything astronomers had encountered before. The prevailing theories about cosmic radio sources couldn't explain such perfect timing. Was it some new, unknown type of star, an entirely different kind of cosmic object? The mystery was profound and exciting. A completely new window into the universe had perhaps just been opened. Through careful analysis and comparison of signals from different parts of the sky, Bell Burnell and Hewish, along with other astronomers, began to piece together the puzzle. They discovered more of these pulsating sources, and their characteristics started to reveal their true nature. The key turned out to be the incredible density of the objects producing the pulses. Only an extremely compact object could spin rapidly enough to produce pulses at millisecond intervals and survive the immense centrifugal forces. The leading candidate quickly became neutron stars, the super-dense remnants of supernova explosions we discussed earlier. It was proposed that these rapidly spinning neutron stars with powerful magnetic fields were emitting beams of radio waves from their poles. As the star rotated, these beams swept across space, and when one happened to sweep across Earth, we detected it as a pulse. The regularity of the pulses was a direct consequence of the incredibly stable rotation of the neutron star itself. While the Little Green Men idea was quickly dismissed, the discovery of pulsars was no less revolutionary. It confirmed the existence of neutron stars, objects whose existence had been theorized but not directly observed before. It opened up an entirely new field of astrophysics, allowing scientists to study matter under extreme conditions and to use pulsars as unique cosmic laboratories for testing theories of gravity and fundamental physics. The initial mystery of the incredibly regular pulses from LGM-1 led to one of the most significant astronomical discoveries of the 20th century, revealing a new class of cosmic objects and showcasing the universe's capacity for producing phenomena that initially defy explanation. From the precisely timed pulses of pulsars, let's turn our attention to another kind of cosmic signal, one that captivated the public imagination like few others in space history. Imagine the 1970s and 80s, the golden age of space probes exploring our solar system. NASA Voyager missions were particularly ambitious. 2 spacecraft launched in 1977 on trajectories that would take them past the outer planets and eventually out of the solar system entirely. These probes were equipped with a suite of scientific instruments, but they also carried something special, something intended to speak across the vast gulf of interstellar space, the Voyager Golden Record. This wasn't just any record, it was a kind of time capsule and cosmic message in a bottle, designed to communicate something about Earth and humanity to any potential extraterrestrial civilization that might one day find the Voyagers. The content was curated by a team led by astronomer Carl Sagan and included sounds and images selected to portray the diversity of life and culture on our planet. Imagine listening to sounds of nature, thunder, waves, birdsong alongside human sounds like greetings in multiple languages, music from different cultures and eras from Bach to Chuck Berry, and even the brainwaves of a young woman. The record also contained 115 images encoded in analog form, depicting everything from our solar system's location to human anatomy, plants, animals, and scenes of human society and technology. Accompanying the record was a stylus and instructions etched onto the cover on how to play it and interpret the information, using universal scientific principles like the location of our solar system relative to pulsars. The mystery surrounding the Golden Record isn't about its origin or purpose. We know exactly where it came from and why it was created. The profound unknown lies in its destination and potential reception. Both Voyager 1 and Voyager 2 are now in interstellar space, having left the heliosphere, the bubble of charged particles from our Sun. They are the furthest human-made objects from Earth, traveling through the vast, dark expanse between star systems. Their trajectories will take them towards different parts of the galaxy, but they won't come close to another star for tens of thousands of years. The records are passive messages, not active broadcasts, relying entirely on chance discovery by a future civilization. So, the enduring mystery of the Voyager Golden Record is this: will it ever be found? And if it is, will the finders be able to interpret its contents? Will the language of science etched onto the cover be truly universal? Will the sounds and images resonate in any way with beings who may have evolved under entirely different conditions and possess entirely different senses and forms of intelligence? Or will it simply become a silent, tumbling artifact in the cosmic void, a testament to a hopeful civilization that once existed on a small blue planet? The Voyager Golden Record is a beautiful, optimistic, and deeply uncertain experiment in interstellar communication, flying silently through the galaxy, carrying our story but with no guarantee of an audience or reply. It embodies the hopeful mystery of reaching out into the dark, not knowing who, if anyone, might be listening. From the silent message of the Golden Record, let's consider an unproven but tantalizing possibility related to another famous mission, the Apollo program that took humans to the moon. While the primary goal was lunar exploration, some have speculated about potential unknown discoveries made during those historic voyages. This brings us to the unsubstantiated, yet widely discussed, notion of unexplained findings on the moon during the Apollo missions. It's important to state upfront that official NASA records and the vast majority of scientific analysis of lunar samples and data have not revealed anything that defies conventional scientific explanation. However, persistent rumors and interpretations have suggested otherwise to some observers. These ideas often stem from interpretations of photographs taken by the astronauts, ambiguous moments in transmissions, or anecdotal accounts that are often taken out of context or lack credible verification. For instance, some have pointed to unusual geological formations in lunar photos as potential evidence of artificial structures, despite geologists identifying them as naturally occurring features shaped by impacts and erosion. Others have speculated about brief communication drops or visual anomalies observed by the astronauts as signs of encountering something unknown, ignoring standard explanations like equipment malfunctions, solar interference, or visual artifacts. One recurring theme in these discussions revolves around the idea of structures or artifacts left on the Moon by a previous, possibly extraterrestrial, civilization. This is sometimes linked to the concept of transient lunar phenomena, which we discussed earlier, suggesting that some of those flashes or glows could be related to active alien technology rather than natural events. However, as noted earlier, the scientific explanations for TLP focus on natural processes like outgassing and meteoroid impacts. The scientific consensus remains firmly rooted in the vast amount of data collected during the Apollo missions, which is consistent with the Moon being a geologically active body in its past, shaped by billions of years of impacts and volcanic activity, but showing no evidence of artificial structures or current alien presence. The lunar samples brought back to Earth have been analyzed by scientists worldwide and provide a consistent picture of the Moon's composition and history, without revealing any anomalies that would suggest non-natural materials or technologies. Despite the lack of credible evidence, the idea of unexplained discoveries on the Moon during Apollo persists in certain circles. This likely speaks to our deep-seated curiosity about what might be hidden on celestial bodies and our desire to find evidence of life beyond Earth, even if it requires interpreting ambiguous data in a specific light. The Apollo missions were monumental achievements transforming our understanding of the Moon, but the persistent rumors of unexplained findings highlight how easily speculation can take root, creating enduring mysteries even in the face of comprehensive scientific data. The real scientific discoveries of Apollo are astonishing enough without needing to invent unsupported narratives. From the potential lunar mysteries, let's direct our gaze towards another type of cosmic visitor, one that arrives with little warning and can leave behind a trail of questions, meteorites that don't quite fit our usual understanding. Most meteorites we find on Earth are stony or metallic, originating from asteroids or occasionally the Moon or Mars. Their composition and structure are generally consistent with the known formation and evolution of bodies within our solar system. However, every now and then, a meteorite is discovered that presents a puzzle, displaying characteristics that are difficult to explain with our current models of solar system formation and composition. One of the classic examples of such a puzzling meteorite is the Allende meteorite, which fell in Mexico in 1969. It's a large, carbonaceous chondrite, a relatively rare type of meteorite that contains organic compounds and calcium-aluminum-rich inclusions or Chi. These CAIs are particularly interesting because they are some of the oldest solid materials in the solar system, formed even before the planets coalesced. While Allende has provided invaluable insights into the early solar system, some of its specific isotopic compositions and mineral structures have proven difficult to fully reconcile with standard models of how materials condensed and aggregated in the solar nebula. It's not that Allende is completely alien, but certain aspects of its chemistry push the boundaries of our current understanding. Another category of perplexing meteorites includes those that show signs of having originated from parent bodies with unexpected geological processes or histories. We've found meteorites that likely came from Mars, blasted off the surface by impacts, and these have told us a great deal about the red planet's composition. But imagine finding a meteorite that appears to have a history of geological activity or water interaction that doesn't easily align with the known histories of asteroids or the inner planets. These outliers, while rare, challenge our assumptions about the diversity of bodies that existed in the early solar system or the processes that might have occurred on them. The mystery isn't necessarily that these meteorites are alien in the sense of coming from outside our solar system, though that's also a rare possibility considered for some objects. The puzzle lies more in what these unusual compositions and structures tell us about the conditions and materials present during the tumultuous period of planet formation. Do they represent remnants of planetesimals that formed in regions of the solar nebula with different temperatures and pressures than we currently model? Could they indicate the existence of parent bodies that underwent unique melting or alteration processes? Studying these anomalous meteorites is like finding a rare, unexpected piece of a jigsaw puzzle. It forces scientists to re-examine their understanding of the whole picture of how our solar system came to be. Each unusual meteorite is a tiny, rocky messenger from the past, occasionally carrying a story that our current scientific language struggles to fully translate, pushing us to refine our theories about the origins of the cosmic neighborhood we call home. Beyond the solid mysteries of meteorites, let's consider something far more ethereal, yet equally baffling: cosmic rays. Imagine tiny, incredibly energetic particles, mostly atomic nuclei, constantly bombarding Earth from all directions in space. These are cosmic rays, and they travel at nearly the speed of light, while many lower-energy cosmic rays originate from within our own Milky Way galaxy, perhaps from supernova remnants or pulsars. The most energetic ones, known as ultra-high-energy cosmic rays or UHECA, present a profound mystery. These particles carry energies far exceeding anything we can generate in even the most powerful particle accelerators on Earth. Where do they come from, and how do they acquire such incredible amounts of energy? The puzzle of UHECA intensified with the discovery of the GZK cutoff, named after physicists Greisen, Zatsepin, and Kuzmin. This theoretical limit predicted that cosmic rays above a certain energy threshold should not be able to travel vast distances through the universe. As these extremely energetic particles travel, they should interact with the photons of the cosmic microwave background radiation, the faint afterglow of the Big Bang that pervades the universe. These interactions would cause the cosmic rays to lose energy, effectively creating a cosmic speed bump for the highest energy particles traveling over long distances. Therefore, UHECA detected on Earth should originate from relatively nearby sources, within about 160 million light-years. However, observations from detectors like the Pierre Auger Observatory in Argentina, the world's largest cosmic ray observatory, have confirmed the existence of cosmic rays with energies above this GZK cutoff. These particles are arriving at Earth, suggesting they must originate from sources within that 160 million light-year radius. The mystery is that we haven't definitively identified powerful enough sources within that volume of space that can accelerate particles to such extreme energies and directions with certainty. Potential candidates include active galactic nuclei which are supermassive black holes at the centers of some galaxies that are actively accreting matter and launching powerful jets, or perhaps the birth of gamma-ray bursts, the most powerful explosions in the universe. But correlating the arrival directions of UHECA with these potential sources has proven challenging. Many UHECA don't seem to point back directly to known energetic objects, partly because magnetic fields in space can deflect their paths, making it difficult to trace them back to their origin. The mystery of UHECA highlights a gap in our understanding of the most extreme particle acceleration processes in the universe. What kind of cosmic engine is capable of imparting such immense energy to individual particles? Are there powerful sources within our cosmic neighborhood that we haven't fully characterized? Or are we missing something fundamental about how these particles propagate through space, or even something about the cosmic microwave background itself at these energies? The existence of particles that defy the expected GZK cutoff and whose origins remain largely unknown, makes ultra-high energy cosmic rays one of the most energetic and perplexing mysteries in astrophysics. From the ultra-energetic particles, let's consider a phenomenon that involves the very fabric of spacetime itself: gravitational waves. Imagine ripples in spacetime, stretching and squeezing everything they pass through, traveling at the speed of light. These gravitational waves were predicted by Albert Einstein's theory of general relativity over a century ago, but they are incredibly weak and notoriously difficult to detect. It wasn't until 2015 that the LIGO scientific collaboration, the Laser Interferometer Gravitational Wave Observatory, made the first direct detection of gravitational waves, a monumental achievement that opened a new window for observing the universe and earned a Nobel Prize. That first detection came from the merger of two black holes, an event that released an unimaginable amount of energy in the form of gravitational waves. While detecting gravitational waves from the dramatic collisions of black holes and neutron stars has become more common since that first detection, there's another theoretical source of gravitational waves that remains elusive and could hold clues to one of the biggest mysteries of all: what happened in the very first moments after the Big Bang. This brings us to the concept of primordial gravitational waves that are thought to have been generated during the period of cosmic inflation. Inflation is a theoretical model that proposes an extremely rapid, exponential expansion of the universe that occurred just fractions of a second after the Big Bang. This period of inflation is invoked to explain several puzzling features of the universe we observe today, such as its remarkable uniformity across vast scales. According to inflationary theory, the enormous energy and rapid expansion during this epoch should have generated a background of gravitational waves, a faint cosmic hum permeating the universe. Detecting these primordial gravitational waves would provide strong evidence supporting the inflationary model and offer a direct probe of the universe at energies far beyond anything we can replicate in laboratories. They would be like fossilized ripples from the very dawn of time. Scientists are searching for evidence of these primordial gravitational waves by looking for their subtle imprint on the cosmic microwave background radiation, specifically in the polarization pattern of this ancient light. In 2014, there was a highly publicized announcement by the BICEP-2 experiment, which claimed to have detected a signature in the CMB polarization that was consistent with primordial gravitational waves. This generated immense excitement, as it seemed to be direct evidence of inflation. However, further analysis, including data from the European Space Agency's Planck satellite, revealed that the signal BICEP-2 detected was likely due to dust within our own Milky Way galaxy, mimicking the expected polarization pattern. This was a disappointing setback, and the search for definitive evidence of primordial gravitational waves continues. The mystery lies in whether these primordial gravitational waves exist, and if so, why they are so difficult to detect. Their detection would not only support inflation but could also provide insights into the fundamental physics that govern the universe at its absolute beginning. The search for this elusive cosmic background of gravitational waves is an ongoing quest, using increasingly sensitive instruments on the ground and potentially in space to listen for the faint whispers of the universe's birth. It's a mystery that connects the largest structures in the cosmos, space-time itself, to the smallest instances of time imaginable, moving from the faint whispers of the universe's birth to a potential whisper from within. Let's consider another unexplained phenomenon that has intrigued solar physicists: coronal heating. Imagine the Sun, our star, a giant ball of incredibly hot plasma. You might expect things to get hotter as you get closer to the core, where nuclear fusion takes place. And indeed, the visible surface of the Sun, the photosphere, has a temperature of about 5,500 degrees Celsius. But then you look at the Sun's atmosphere, its corona, which extends millions of kilometers into space, and you find something completely counterintuitive. The corona is incredibly hot, reaching temperatures of over 1,000,000 degrees Celsius, sometimes even tens of millions of degrees during solar flares. This is orders of magnitude hotter than the surface below it. This stark temperature difference represents the fundamental puzzle of coronal heating. Why is the Sun's atmosphere so much hotter than its surface? This isn't just a minor discrepancy, it's a major mystery in solar physics. It's like seeing water boiling rapidly above a block of ice. There must be a powerful mechanism at play that is depositing vast amounts of energy into the corona, away from the primary heat source, the Sun's core. Scientists have been trying to solve this mystery for decades, proposing various theories to explain this extreme heating. Two main contenders dominate the debate: wave heating and magnetic reconnection. The wave heating theory suggests that energy is transported from the Sun's interior up into the corona by various types of waves, such as acoustic waves or Alfvén waves, a type of wave that travels through plasma following magnetic field lines. These waves, generated within or below the photosphere, travel outwards and somehow release their energy in the corona, converting wave energy into thermal energy and thus heating the plasma. Think of it like sound waves causing vibrations that generate heat, but on a massive stellar scale. The magnetic reconnection theory, on the other hand, focuses on the Sun's powerful and complex magnetic field. The Sun is a highly magnetized, dynamic object, with magnetic field lines constantly emerging from and retracting back into the surface, creating intricate and tangled structures in the corona. Magnetic reconnection occurs when these magnetic field lines break and then reconnect in a different configuration. This process is incredibly energetic, converting magnetic energy into kinetic and thermal energy, accelerating particles and heating the surrounding plasma to extreme temperatures. It's like snapping a stretched rubber band, but with magnetic field lines instead, releasing explosive energy. This process is thought to be responsible for dramatic events like solar flares and coronal mass ejections, but the question is whether it also provides a constant, steady source of heating for the ambient corona. Observational evidence from solar telescopes and spacecraft like NASA's Solar Dynamics Observatory and the Parker Solar Probe is providing unprecedented details of the Sun's atmosphere, allowing scientists to study these processes up close. These observations show evidence supporting both wave activity and magnetic reconnection happening in the corona. However, precisely how much energy each mechanism contributes to the overall coronal heating budget, and exactly where and how that energy is deposited, are still subjects of intense research and debate. The mystery of coronal heating remains one of the most significant unsolved problems in solar physics, essential to understanding the behavior of our own star and stars throughout the universe, highlighting that even the most familiar object in the sky holds fundamental secrets about energy transfer in extreme environments. Beyond the visible flashes and glows of transient lunar phenomena, there are also intriguing reports of unusual heat signatures detected on the Moon's surface. These aren't the widespread temperature changes you'd expect from the Sun's warming and cooling of the lunar surface, but localized spots showing temporary, inexplicable increases in temperature. Imagine thermal sensors on orbiters or even instruments on the surface registering a sudden hotspot that doesn't align with solar illumination or known geological features. These are sometimes referred to as lunar transient heat phenomena, a less discussed but equally perplexing counterpart to the visual TLP events. While less frequently reported than the visual flashes, observations of unusual thermal spikes have been made over the years, sometimes correlating with areas where visual TLP has also been seen. These observations are challenging because they require specific instrumentation to be pointed at the right place at the right time, and the events appear to be brief and unpredictable. The data is often limited, making it difficult to confirm the observations or gather enough information to understand the nature of the heat source. Is it a sudden burst of heat, a lingering warmth, or something else entirely? The sparse and transient nature of these reported thermal anomalies makes them incredibly difficult to study systematically. Scientists have grappled with potential explanations for these transient hotspots, none of which have been definitively proven. One possibility involves localized outgassing from beneath the lunar surface. If gases are released through a vent or fissure, they could potentially carry heat from the moon's interior, causing a temporary rise in temperature in that specific area. Another idea is related to subsurface geological activity, perhaps very weak seismic events or minor movements along faults that generate friction and heat, though the moon is generally considered geologically quiet today. Some speculate about exotic subsurface chemical reactions that might release energy in a localized fashion. However, without more direct evidence or repeated observations of these thermal anomalies, it's hard to determine the exact mechanism. These mysterious lunar heat signatures offer another layer of complexity to the seemingly dormant moon, suggesting that there may still be unknown, localized processes occurring beneath its surface that we are yet to fully understand. Leaving enigmatic heat spots behind, let's follow the trails of our space pioneers, two sets of spacecraft that have ventured further from Earth than any before them, the Pioneer and Voyager probes. As these hardy explorers journeyed out of the solar system, past the orbits of the planets, something unexpected began to happen. Scientists tracking their trajectories using incredibly precise Doppler measurements noticed a tiny, persistent, and baffling anomaly. Both Pioneer 10 and 11, and later the Voyager 1 and 2 spacecraft, despite traveling in different directions and having different designs, appeared to be experiencing a very slight, unexplained acceleration directed back towards the Sun. It was a minuscule acceleration, about 1/1000th of a g, the acceleration due to Earth's gravity, but it was undeniable and it wasn't accounted for by the gravitational pull of the Sun, planets, or other known solar system objects. This became known as the Pioneer anomaly, though it was also observed in the Voyagers to a lesser extent. Think about it, you expect gravity to slow a spacecraft down as it heads away from the Sun, but these probes seem to be getting a gentle, unasked-for nudge back home. This puzzling observation triggered an extensive and meticulous investigation by scientists and engineers. They went back and analyzed decades of tracking data from all four probes, checking every possible known effect that could be causing this apparent acceleration. They considered everything from the tiny, subtle gravitational pull of Kuiper belt objects to potential errors in calibration of the tracking equipment. They painstakingly modeled the effects of solar radiation pressure, the faint push of sunlight itself, and the thermal radiation emitted by the spacecraft's own power sources and instruments, which could create a tiny, directed force. They even looked at the possibility of minute leaks of propellant from the thrusters, which could provide a tiny, unwanted thrust. Every known, conventional explanation was examined, quantified, and one by one found insufficient to fully explain the observed anomaly. The mystery persisted. While a definitive, universally accepted explanation for the anomalous acceleration of the Pioneer and Voyager probes remains elusive, several potential explanations have been proposed over the years, though none have completely resolved the puzzle. One leading idea, particularly for the Pioneer probes which showed the strongest effect, points to the anisotropic thermal radiation from the spacecraft themselves. The probes were powered by radioisotope thermoelectric generators (RTG), which produce heat. If this heat wasn't radiated perfectly symmetrically in all directions, the slight imbalance could create a net force. Later detailed analysis of the Pioneer spacecraft's thermal properties suggested this might account for a significant portion, perhaps even all, of the observed acceleration, though complexities in modeling the heat distribution make it hard to be absolutely certain. Other, more speculative, ideas have included modifications to the laws of gravity at vast distances or interactions with dark matter, though these remain far from proven. The fact that the Voyager probes with different designs and thermal characteristics showed a smaller effect also lends some weight to a thermal explanation. However, the precise contribution of different factors and whether all of the anomaly is truly explained by thermal effects is still debated in the scientific community. The Pioneer anomaly, while potentially having a mundane explanation rooted in thermal physics, served as a fascinating puzzle for decades, pushing scientists to consider every possibility and reminding us that even when tracking our most distant explorers, unexpected forces can be at play. Stepping back into the realm of potential alien visitors, though this time a purely natural object, let's discuss a celestial traveler that caused a stir when it zipped through our solar system. In 2017, astronomers using the Pan-STARRS telescope in Hawaii detected something unusual, a faint point of light moving across the sky at a speed that indicated it wasn't orbiting our sun. This was the first observed interstellar object passing through our solar system, a visitor from another star system entirely. It was given the Hawaiian name Oumuamua, meaning scout. What made Oumuamua so fascinating and ultimately so mysterious wasn't just its interstellar origin, but its bizarre characteristics. As astronomers tracked its path and observed its brightness changing as it tumbled through space, they realized it had an incredibly elongated shape, perhaps 10 times longer than it was wide, like a cosmic cigar or pancake. This shape was unlike any comet or asteroid we'd ever seen within our own solar system. Furthermore, as it sped away from the sun, it showed a slight, non-gravitational acceleration. This kind of acceleration is sometimes seen in comets as gases are expelled from their icy surfaces, creating a tiny rocket effect. However, Oumuamua didn't show any visible signs of outgassing or a coma like a typical comet. It was leaving our solar system as silently and mysteriously as it arrived. The combination of its unusual shape, interstellar origin, and baffling non-gravitational acceleration prompted significant scientific debate and led to various theories about what Oumuamua could be. Was it a hydrogen iceberg, a chunk of frozen hydrogen that evaporated silently? Was it a piece of a shattered planet or a new class of interstellar object we hadn't anticipated? While most explanations focused on natural phenomena, the sheer strangeness of Oumuamua, coupled with the lack of definitive evidence for any of the proposed natural origins, led some to consider a more exotic possibility. Could it be an artificial object, perhaps a probe sent by an alien civilization? This idea, championed by some researchers, though highly controversial and largely dismissed by the wider scientific community due to lack of evidence, highlighted just how unusual Oumuamua was and how it defied easy categorization based on our existing knowledge of cosmic objects. Ultimately, Oumuamua was only visible for a short time before speeding away into the outer reaches of the solar system and beyond, making further detailed observations impossible. We were left with tantalizing data but no definitive answers. Its passage through our cosmic neighborhood was a brief, unexpected encounter with the unknown, highlighting the possibility that interstellar space might be filled with objects unlike any we've encountered before, and reminding us that the universe can still throw us curveballs that challenge our assumptions and spark exciting, if sometimes speculative, ideas about what else might be out there. Leaving behind the fleeting visit of an interstellar object, let's turn our attention to a star that has been behaving in a truly bizarre way, sparking intense scientific curiosity and public imagination. We're talking about Tabby's star, officially known as KIC 8462852, located about 1,470 light-years away in the constellation Cygnus. This is a star that captured the astronomical community's attention back in 2015, thanks to data from the Kepler Space Telescope. Kepler's primary mission was to look for exoplanets by monitoring the brightness of thousands of stars, watching for tiny dips in light that occur when a planet passes in front of its star. But Tabby's star wasn't showing tiny, regular dips. It was showing something far more dramatic and irregular. The light from Tabby's star was dimming significantly and erratically, sometimes dropping by as much as 22%. And these weren't periodic dips like you'd expect from orbiting planets. The dimming events were unpredictable, varied in duration, and inconsistent in how much light was blocked. Imagine watching a star and seeing its light suddenly plunge, then recover, then plunge again days or weeks later, but in a completely different pattern. This highly anomalous behavior immediately ruled out a simple explanation like a transiting planet. What could possibly be causing such massive, irregular blockages of starlight? The strange light curve of Tabby's star prompted astronomers to propose numerous hypotheses, ranging from the mundane to the truly extraordinary. Initial conventional explanations focused on natural phenomena. One leading idea was that the star was being orbited by a swarm of comets. If a huge cloud of comets had been disrupted, perhaps by the star's gravity or a passing star, they could be breaking up and producing vast amounts of dust and debris, which would then periodically pass in front of the star as they orbited, causing the observed dimming. While plausible, this theory required an enormous number of comets to create such significant dimming events, and it wasn't entirely clear if the dust distribution from such a swarm truly matched the complex dimming patterns observed. Other natural explanations included the possibility of the star undergoing strange internal processes, or perhaps even having a ring system so vast it could block light, though none of these fully fit all the data. Because conventional explanations struggled to fully account for the star's peculiar behavior, some scientists, while stressing its highly speculative nature, raised the possibility of something far more exciting: alien megastructures. The idea, perhaps most famously associated with physicist Freeman Dyson's concept of a Dyson sphere, is that an advanced civilization might build colossal structures like massive solar energy collectors or habitats around their star to harness its energy. If such structures were under construction or in disarray, they could potentially produce the kind of large, irregular dimming patterns seen from Tabby's star. This notion, while requiring an advanced civilization constructing something on a scale almost beyond our comprehension, captured the public's imagination and became the most talked about explanation for the star's odd behavior. Despite the allure of the alien megastructure idea, the vast majority of current scientific thinking favors natural explanations, even if they are complex or involve phenomena we haven't fully characterized. Subsequent observations of Tabby's star have revealed that the dimming is more prominent at certain wavelengths of light than others, which is more consistent with the presence of dust than with opaque solid structures. While the exact nature and origin of that dust or whatever else is causing the dimming are still being researched, the evidence currently points away from artificial structures. Yet, the mystery of Tabby's star and its erratic dimming remains a compelling example of a celestial phenomenon that initially defied easy explanation, pushing the boundaries of our understanding and briefly allowing for the tantalizing, though unproven, possibility of something truly alien at work. Observing this star continues to be a source of scientific discovery. Moving back to the protective layers surrounding our own planet, let's discuss an area that poses a unique challenge for spacecraft passing through it: the South Atlantic Anomaly. Imagine Earth's magnetic field as a giant shield, protecting us from harmful radiation streaming from the sun and outer space. This magnetic field traps charged particles, forming regions known as the Van Allen radiation belts, some thousands of kilometers above the surface. However, due to the offset between Earth's geographic north and the planet's magnetic north pole, there's a specific region over the South Atlantic Ocean where the inner Van Allen belt dips much closer to the Earth, sometimes reaching altitudes as low as a few hundred kilometers. This lower altitude region is the South Atlantic Anomaly. Passing through the South Atlantic Anomaly is particularly risky for satellites and spacecraft, including the International Space Station. Because the radiation belt is much lower here, spacecraft in low Earth orbit have to travel through a higher concentration of energetic protons and electrons. These high-energy particles can cause significant problems. They can damage electronic components, leading to temporary malfunctions or even permanent failures. They can also interfere with scientific instruments, causing spurious data or affecting measurements. Astronauts on the International Space Station, which passes through the anomaly multiple times a day, are exposed to increased radiation levels in this region, necessitating additional shielding and monitoring to minimize their exposure. It's like a specific hazardous patch of space that we must navigate carefully. Understanding why this anomaly exists and how it behaves is an ongoing scientific endeavor. The South Atlantic anomaly is a direct consequence of the intricate and constantly changing dynamics of Earth's magnetic field, which is generated by the movement of molten iron in our planet's core. This process isn't perfectly stable or symmetrical. The fact that the magnetic north and south poles don't align perfectly with the geographic poles, and that the magnetic field itself is slowly drifting and changing in strength, directly influences the shape and position of the Van Allen belts. The magnetic field lines in the South Atlantic region happen to be weaker, allowing the belt to drop closer to Earth. Researchers constantly monitor the size, shape, and intensity of the anomaly using data from various satellites. Studying its changes over time provides crucial information about the complex processes happening deep within Earth's core, as well as helping mission planners anticipate and mitigate the risks for spacecraft. The South Atlantic anomaly serves as a tangible reminder that even the protective shield of our planet's magnetic field has its weak spots, presenting a persistent challenge for our activities in low Earth orbit and highlighting the dynamic nature of our planetary defense system. Shifting our focus from magnetic anomalies to atmospheric mysteries, let's talk about a gas that on Earth is strongly associated with life, and whose presence and strange behavior on Mars has sparked intense scientific debate: methane. For years, various missions and ground-based telescopes have detected methane in the thin Martian atmosphere. While the amounts are tiny compared to Earth's atmosphere, it's the way the methane behaves on Mars that is truly puzzling. We're not talking about a constant, uniform level of the gas. Instead, observations have shown significant seasonal and even localized fluctuations in its concentration. Imagine measuring methane levels in one spot on Mars and finding them higher in the summer and lower in the winter, or detecting surprising plumes of methane in specific regions that weren't there before. This variability is the heart of the Martian methane mystery. So, what could be producing this methane and causing these perplexing fluctuations? On Earth, most methane is produced by biological processes, microbes in swamps, the digestive systems of animals, etc. This immediately raises the tantalizing, though highly speculative, possibility of life on Mars. Could simple Martian microbes, perhaps existing underground where they are protected from the harsh surface radiation, be producing this methane as a byproduct of their metabolism? While exciting, this is just one of several potential explanations. Methane can also be produced by non-biological geological processes. For example, hydrothermal activity, where water reacts with certain rocks, could release methane. Even though Mars is not currently geologically active like Earth, past or even present subsurface hydrothermal processes could potentially be a source. Another possibility is that methane is being delivered to Mars by comets or asteroids that impact the planet, although this wouldn't easily explain the observed fluctuations. The difficulty lies in explaining the fluctuations. If methane were simply seeping out from a constant geological source, you might expect a more steady level. Seasonal changes in temperature or atmospheric circulation could play a role, perhaps causing methane trapped underground to be released at different rates, or influencing how the gas is distributed in the atmosphere. However, current climate models for Mars struggle to fully account for the magnitude and speed of the observed variations. The fact that methane seems to appear and disappear in certain areas and change with the seasons points to either a dynamic release mechanism or a rapid process that destroys the methane. While sunlight can break down methane over time, the observed fluctuations seem too fast for this process alone to be the sole explanation. Each new detection and every measurement of its variability adds another piece to this complex puzzle. The presence and baffling behavior of methane on Mars continues to be a focal point in the search for life beyond Earth, forcing scientists to consider all possibilities, from the purely geological to the potentially biological, in their quest to understand the red planet's atmosphere and its subsurface environment. Shifting our focus from the rocky surface of Mars and its puzzling atmospheric gases, let's venture out to the outer solar system, to one of Jupiter's 4 largest moons, Europa. This icy world has long been a prime target in the search for life beyond Earth, not because of its frigid surface, but because evidence strongly suggests there's a vast ocean of liquid water hidden beneath its icy crust. Imagine a saltwater ocean, potentially twice the volume of all of Earth's oceans combined, locked away beneath miles of ice. This subsurface ocean makes Europa one of the most promising places in the solar system to look for conditions suitable for life. But how do we study an ocean hidden beneath a thick shell of ice? This is where the mystery of Europa's potential plumes comes in. Over the years, observations from spacecraft like the Hubble Space Telescope have hinted at the possibility of geysers or plumes of water vapor erupting from the moon's surface, shooting high into space. Think of it like Yellowstone geysers, but on an alien moon, potentially blasting water from the subsurface ocean thousands of kilometers above Europa's surface. The first tantalizing hint of these plumes came in 2012 from Hubble data, suggesting water vapor over Europa's south polar region. Later observations in 2016 and 2017 provided further, though still indirect, evidence of these potential eruptions. These detections were incredibly exciting because, if confirmed, these plumes would offer a direct way to sample Europa's subsurface ocean without having to drill through miles of ice, a technological feat far beyond our current capabilities. The significance of these plumes cannot be overstated. If water from the subsurface ocean is indeed making its way to the surface, it could potentially carry with it clues about the ocean's composition, including salts, organic molecules, or even evidence of microbial life if it exists. Studying the material in these plumes could provide crucial insights into the habitability of Europa's ocean and whether the ingredients for life are present. However, confirming the existence of these plumes and understanding their origin has proven challenging. The plumes appear to be intermittent, making them difficult to catch with telescopes from afar. Furthermore, the detections so far have been based on subtle signals, not direct visual confirmation like the majestic geysers of Saturn's moon Enceladus, which were clearly photographed by the Cassini mission. The origin of these sporadic plumes is also part of the mystery. Are they driven by volcanic activity on the seafloor, a sign of ongoing geological processes within Europa? Could they be caused by tidal forces from Jupiter, which intensely stretches and squeezes Europa as it orbits, generating heat and potentially cracking the ice crust and pushing water upwards? Or are they related to other processes happening within the ice shell itself? Upcoming missions like NASA Europa Clipper, which is scheduled to arrive at Jupiter in the 2030s, are specifically designed to investigate Europa's ocean and ice shell, and are equipped to search for and even fly through these potential plumes, analyzing their composition directly. The mystery of Europa's plumes highlights the dynamic nature of this intriguing moon, and holds the potential key to unlocking the secrets of its hidden ocean and its potential for hosting life. Beyond the individual mysteries of stars and moons, let's consider something on a truly colossal scale: a potential movement of matter across vast stretches of the universe that might not fit expected patterns. This brings us to a controversial concept known as the dark flow. Imagine not just individual galaxies, but entire clusters of galaxies, massive groupings containing hundreds or even thousands of galaxies all moving together in a coherent direction, a kind of cosmic river flowing across space. While the universe is generally expanding, pushing galaxies apart according to Hubble's law, scientists measure something called peculiar velocities, the motion of galaxies or clusters relative to this general expansion. These peculiar velocities are expected to be influenced by the gravitational pull of nearby large structures like superclusters. However, some early observations suggested something more, a component of this motion that seemed directed towards a specific region of the sky, a bulk flow that appeared too large and too coordinated to be explained simply by the gravitational pull of known structures. This was the initial idea behind the dark flow, a claim that there's a non-random, directed movement of galaxy clusters on immense scales. The observations that initially suggested this dark flow were based on measuring the peculiar velocities of galaxy clusters using the kinetic Sunyaev-Zeldovich effect, a subtle distortion of the cosmic microwave background radiation as it passes through hot gas in galaxy clusters that are moving towards or away from us. By measuring this effect for a large sample of clusters, astronomers in the mid-2000s claimed to see a preferred direction in their movement towards a region roughly between the constellations Centaurus and Vela. This wasn't just a few clusters. The effect seemed to be present across a significant volume of the observable universe included in their study. The magnitude and direction of this apparent bulk flow were difficult to reconcile with the standard cosmological model, which predicts that peculiar velocities on such large scales should be more randomly distributed, influenced locally by the gravitational pull of the cosmic web of matter. The idea of a coordinated flow on such immense scales, potentially driven by gravitational influences outside the observable universe, was both intriguing and highly debated. Since those initial claims, subsequent studies attempting to confirm or refute the existence of the dark flow have yielded mixed results. Some studies, using different data sets or methodologies, have found evidence consistent with a bulk flow, though often with variations in its magnitude or direction. Others have failed to detect a statistically significant coherent flow that cannot be explained by known gravitational influences within the observable universe. The difficulty lies in the challenges of accurately measuring peculiar velocities for large numbers of distant galaxy clusters, and in distinguishing a true large-scale flow from the gravitational effects of known, though sometimes poorly mapped, structures. The complex interplay of gravity on vast scales makes it difficult to isolate a potential dark flow signal. While the initial strong claims of a large, directed cosmic river have been tempered by the inconclusive results of follow-up studies, the idea of a coherent movement of galaxy clusters on scales larger than expected by the standard model remains a fascinating and unresolved question. Whether the dark flow is a real, albeit subtle, phenomenon suggesting gravitational influences from beyond our observable horizon, or simply a result of measurement uncertainties and the complexities of cosmic structure formation, is a mystery that continues to be explored by cosmologists, reminding us that our understanding of the largest structures and motions in the universe is still a work in progress. From the potential large-scale motions of galaxies across the cosmos, let's look at a feature on the absolute largest scale. We can observe a pattern in the faint, ancient light that fills the universe. This brings us to one of the most intriguing anomalies observed in the cosmic microwave background radiation, often called the cold spot. Imagine looking at a baby photo of the universe taken when it was only about 380,000 years old. That's essentially what the cosmic microwave background, or CMB, is. It's the afterglow of the Big Bang, the oldest light we can detect, and it permeates the entire universe. This radiation is incredibly uniform in temperature across the sky, a testament to how smoothly distributed matter and energy were in the early universe. However, when scientists analyzed the detailed maps of the CMB captured by missions like the WMAP and Planck satellites, they noticed subtle variations, tiny hot and cold spots that correspond to slight density fluctuations in the early universe, the seeds that would eventually grow into galaxies and clusters. But within this expected pattern of variations, one feature stood out dramatically: a vast region that is significantly colder than its surroundings. This is the CMB cold spot. Located in the southern constellation Eridanus, the cold spot is a patch of sky spanning about 5 degrees across roughly 10 times the diameter of the full moon. Within this area, the CMB temperature is noticeably lower than the average temperature of the surrounding CMB. While there are always expected fluctuations in the CMB temperature due to the uneven distribution of matter in the early universe, the cold spot is simply too large and too cold to be easily explained by these standard fluctuations based on our current understanding of cosmology. Its existence challenges the predictions of the standard cosmological model, leading scientists to consider various explanations for this puzzling anomaly. It's like seeing an unusually deep valley in an otherwise gently rolling landscape, prompting you to wonder how it got there. What could cause such a large, unusually cold region in the ancient light of the universe? Several theories have been proposed, each with different implications for our understanding of the cosmos. One prominent explanation suggests that the cold spot is caused by a massive void, a vast region of space with significantly fewer galaxies and less dark matter than average, located between us and the part of the CMB where the cold spot is observed. As light from the CMB passes through such a void, it can lose energy due to a phenomenon called the integrated Sachs-Wolf effect, making that region appear colder than it actually is. Think of light having to climb out of a gravitational potential created by matter. If there's less matter in a region, the potential is shallower and the light loses less energy. But if there's a void, the gravitational pull is slightly weaker, and the light actually gains a tiny bit of energy as it enters the void and then loses more as it leaves, resulting in a net loss of energy over journey through the void. While large voids are expected in the universe, astronomers have searched for a single, sufficiently large and empty void in the direction of the cold spot, and haven't found one that fully explains the magnitude of the temperature drop. Perhaps it's a collection of smaller voids, but even that requires specific conditions. Other, more speculative, theories about the cold spot venture into less conventional territory. One idea is that it could be the imprint of a collision with another universe, a bubble universe that bumped into ours during the inflationary period after the Big Bang. This is a highly theoretical concept rooted in some models of eternal inflation, but it suggests the cold spot could be a rare, tangible sign of the existence of other universes. Another possibility is that the cold spot is an indication that our standard cosmological model is incomplete, perhaps requiring modifications to the laws of physics on the largest scales. The fact that this significant anomaly exists in the most detailed maps of the early universe we have is what makes it so important and so mysterious. It serves as a potential crack in our current understanding, a feature that encourages us to look for new physics or more complex explanations for the structure and evolution of the cosmos on its grandest scales. The CMB cold spot is a cosmic puzzle etched in ancient light, urging us to refine our models and look for the true cause of this significant deviation from the expected uniformity of the infant universe. From the largest structures in the cosmos, let's shift our gaze to a single, familiar star that briefly puzzled astronomers and stargazers alike, Betelgeuse. You've likely seen this star, the bright red giant in the shoulder of the constellation Orion. It's a variable star, meaning its brightness naturally fluctuates over time. But in late 2019 and early 2020, Betelgeuse did something completely unexpected. It dimmed dramatically, reaching a historic low in brightness that hadn't been seen in a generation. Imagine a star you've known your whole life suddenly appearing significantly fainter in the night sky. This rapid and profound dimming of Betelgeuse, a star we thought we understood, quickly became headline news and a major topic of scientific investigation. What was going on with this familiar celestial neighbor? The reason this dimming was so unusual for Betelgeuse, despite being a variable star, lies in the magnitude and speed of the change. While its brightness typically varies over cycles of hundreds of days, the 2019 to 2020 dimming was much deeper and faster than these usual fluctuations. Betelgeuse is a red supergiant, an enormous star nearing the end of its life. These stars are known to be unstable and puff off material, but the scale of this dimming suggested something more extreme was happening. Initial speculation ran wild. Was Betelgeuse about to explode as a supernova? While its eventual fate is indeed a supernova, astronomers quickly calculated that this dimming event didn't fit the profile of an imminent explosion. A supernova is a sudden, terminal event, and the dimming seemed more protracted and recoverable. The mystery was trying to pinpoint the specific, unusual process that caused such a significant blockage of the star's light. Through intense observation using multiple telescopes, both on the ground and in space, scientists began to piece together a leading explanation for Betelgeuse's mysterious dimming. The most compelling theory suggests that the star experienced a massive stellar eruption, a kind of supercoronal mass ejection far exceeding anything seen from our own Sun. This eruption likely expelled a significant amount of stellar material, a blob of high-density plasma, outwards from the star's surface. As this material moved away from Betelgeuse, it cooled and condensed, forming a cloud of dust. It was this newly formed cloud of dust, drifting in front of the star from our perspective, that is believed to have blocked a substantial portion of the star's light, causing the unprecedented dimming we observed. This stellar eruption and subsequent dust formation was an event on a scale rarely, if ever, observed directly on another star. While this explanation is currently the most favored, it doesn't eliminate all the mystery. The precise mechanism of the eruption itself, why it was so powerful at that particular time, and how the dust cloud formed and dissipated are still subjects of ongoing study. The Betelgeuse dimming event served as a dramatic reminder that even well-studied stars can hold surprises, showcasing dynamic processes we are just beginning to understand and providing an unprecedented opportunity to study stellar evolution in real time. From the changing brightness of a single, distant star, let's return to our own solar system, to a small celestial body that has presented astronomers with a truly unique and perplexing orbital puzzle. Recently designated as ZUZV, this is no ordinary asteroid. Its trajectory is so bizarre and chaotic that it's being influenced by the gravitational pull of two planets, both Earth and Venus. Imagine an object caught in a cosmic tug of war between our planet and our closest planetary neighbor. This makes ZUZV's path through the solar system incredibly complex and difficult to predict with long-term certainty. Its orbit isn't a neat ellipse like most asteroids. Instead, it traces a looping, unpredictable dance that brings it sometimes closer to Earth's orbit, and at other times within the gravitational sphere of influence of Venus. The unusual orbit of ZUZV is a fascinating example of the intricate gravitational dynamics at play in a multi-body system. While the Sun's gravity is the dominant force, the cumulative gravitational nudges from Earth, Venus, and even other planets subtly but significantly alter ZUZV's path over time. This means that its orbit isn't stable over long timescales. It's what scientists call chaotic small uncertainties in our measurements of its current position and velocity, can lead to large differences in predictions of where it will be hundreds or thousands of years from now. Think of trying to predict the exact path of a leaf caught in a complex swirling current. It's incredibly sensitive to the initial conditions, Pinpointing ZUZV's precise long-term trajectory requires sophisticated computer simulations that factor in the gravitational forces of multiple planets, and even then, the further out you project, the more uncertain the prediction becomes. Understanding the orbital dynamics of a celestial body like ZUZV is crucial, not just for the intellectual pursuit of mapping our solar system, but also for the practical implications of potential future close approaches. While ZUZV is not currently considered a threat, its unpredictable nature means that ongoing monitoring and refined orbital calculations are essential. Astronomers are actively working to gather more precise data on ZUZV's position and movement to improve the accuracy of their orbital models. Each new observation helps to constrain the possibilities and reduce the chaotic uncertainty. Studying objects like ZUZV also provides valuable insights into the complex dance of gravity in our solar system and how the interactions between planets can shape the paths of smaller bodies, potentially shedding light on the origins and evolution of some of the asteroids in our vicinity. This little space rock caught between two worlds presents a compelling mystery in orbital mechanics right here in our cosmic backyard. As we draw our cosmic inventory to a close, having touched upon 25 moments that have left astronomers scratching their heads, one thing is abundantly clear: space history is not a linear narrative of solved puzzles. It's a tapestry woven with threads of the known and vast swaths of the unknown. We've traversed from fleeting radio signals that hint at intelligence or extreme physics, to the devastating, craterless impact of Tunguska, to the persistent, silent vigil of the Black Knight myth. We've considered the subtle dances of light on our moon, the immense, invisible structures of dark matter and dark energy shaping the universe, and the profound silence that underscores the Fermi paradox. The universe, as revealed by these baffling events, is far more complex, dynamic, and mysterious than we often give it credit for. Each anomaly, whether it's an unexpected dimming star, an object with a chaotic orbit, or patterns in the ancient light of the cosmos that shouldn't be there, serves as a powerful reminder of how much is still left to explore and understand. These aren't just isolated oddities, they are signposts pointing towards potential new physics, undiscovered cosmic phenomena, or even, perhaps, the presence of life beyond our planet. The pursuit of explaining these baffling events is what drives scientific discovery, pushing the boundaries of our technology, our theories, and our imagination. What do you make of these interstellar enigmas? Were there any that particularly captured your imagination or led you down a rabbit hole of research? We'd love to hear your thoughts, theories, or even other unexplained cosmic events you know about in the comments section below. If you found this journey through space history's most baffling moments as fascinating as we did, please hit that like button. It truly helps the channel. And for more explorations into the weird, the wonderful, and the unexplainable corners of the cosmos, make sure you're subscribed and have notifications turned on so you don't miss our next deep dive.